Now some of this is just interpreting, right? I want to look at this and I would say, in which section is the cart accelerating? So this one, meters and seconds. I don't really, an acceleration is meters per second squared. So I can't really take meters times seconds or meters divided by seconds and get that answer. This one I just kind of have to interpret this. What I'm looking at here is I know that meters per second, if I divide this, gives me my velocity. So if I have a graph of meters per second and I want to look at what point would the velocity be increasing, meters per second from here to here means that I would have velocity increasing at a constant rate if it was a straight line, okay? But what I'm getting is this curved line. So if you have a meters versus seconds line and there's a curved line, that's a sign of acceleration. So in this case, from B to C, I have this exponential graph. And you think about meters per second squared, it should be some sort of exponential graph in there. So this tells me B and C is accelerating and D and E is deaccelerating. So both of these are accelerating. One has a positive, one has kind of a negative slope on that thing. So for this one, I'm going to say which sections is going to be B to C and D to E. In which case is the cart not moving? Well, this is just distance right here. So all you have to do is find out some point where, like here, when you're going for 10 seconds, it stays at 10 meters. Yeah, that pretty much implies that the thing is not moving. Okay, and also E to F. It's at 60 meters here, and it's at 60 meters here. So over the course of 10 seconds, neither one of those cases did the cart, it had the same distance, but change in time, so that implies it's not moving. So we want to go A and B and E and F. Okay, in which case is the cart moving backwards? Okay, so I want to know which case is the cart moving backwards, and really all I'm doing is saying, okay, if I'm at 60 and all of a sudden, 10 seconds later, I'm at 30, okay, this implies that I must be moving backwards, okay? So if you have a line, a slope like this, and it's going down, this implies some sort of negative, so we would say F and G. Between F and G, it would be a negative slope. Okay, in which section is the cart's instantaneous velocity at any time equal to its average velocity? So remember, I talked about this briefly about how to get instantaneous velocity. So if I have some sort of weird average velocity where you're going to Michigan City, or you're traveling and you're going faster and slower and faster and slower and faster and slower, it's very hard to get instant velocity. But if I'm moving at a constant velocity, then my instantaneous velocity should equal my average velocity. And so if I look at this, I'm saying, well, I have no velocity here. I have velocity here, but it keeps getting faster and faster and faster. So that means that my average velocity is going to be different than instantaneous, because in order to determine instantaneous, if I'm going to determine my instantaneous velocity of this point right here, all I have to do is make a line tangent to the curve, right? And so then I would interpret it differently. But if I'm looking for a point where average velocity equals instantaneous velocity, that tangent has to be the same as my original curve. So what I'm looking for is something like this, C and D, because my tangent to C and D is equal to the original slope. So we know for sure C and D, and then we also know for sure F and G. So even though this is getting slower, it's the same for both the average and the instantaneous. And F to G. Okay. What is the velocity of the cart in these sections? So to get velocity, I need meters divided by seconds. So meters divided by seconds, if I take the y, which is m, divided by the t, which is s, that means y divided by s, or x I should say, is equal to my the answer that I want. So this is going to be slope. So all I have to do is figure out slope, and I can get velocity. So let's try this. A to B. I'm going to take 10 minus 10 minus 10, and we'll divide it by 10, and we get 0. Okay? Next one, C to D. I'm going to go from this point, which is 50 meters, and I'm going to subtract out, this is my y2, my y1, which is 40, and then each one of these increments is 5 seconds, so 5, 10, 15, and I get like 0.67 or so 0.67 meter, and these are all meters per second. Okay, E to F. At this point, I'm going from 60 minus 60 divided by, well, who cares, because the top part is 0, so this is also 0. And then the bottom one, I'm going from, since this is, I'm going from 30, and I'm subtracting 60, so this is, and it's going down, so we should know there's some sort of a negative slope or negative velocity, and then I'm dividing that by 510. So this should equal negative 3.0 meters per second. Okay, and then the last question is, how far does the cart move in sections B and C and in E and F? Okay, so with that, since I have distance, this is a pretty easy graph to read. You really don't need my help with this probably. If you're going from B to C, well, distance implies that I'm just climbing up the y graph. And so if I'm starting at 10 here and I'm climbing to 40, 40 minus 10 means that I am going 30 meters. And from E to F, my distance does not change, right? So in that case, it's 0. Okay, I probably make one more of these graphs because I want to be able to have a little bit more practice with interpreting graphs that are a little bit complicated. But this should get you through the basics of kinematics graphs.